Okay. Hello, everyone, and welcome to the London Machine Learning Meetup. I'm Giuseppe from Evolution AI, and together with Alessio, I'll be hosting today's session. So today we have Anima Anandkumar, who's going to talk to us about the convergence of AI, simulation, and high-performance computing. And the talk is going to be mediated by Edgar Schönfeld, who is a PhD student at the Bosch Institute for AI. So as usual, you can ask questions using the Q&A tool. So you can ask them at any point during the talk, and we'll try to have like some moments during the talk where you can stop and ask questions. If you have any issues or anything that you need to communicate with us, please use the chat. And as usual, the talk is going to be recorded and uploaded to our YouTube channel. Okay, so without further ado, I'll leave the stage to Anima.
Thank you. Let's see now. Okay, now there. Yeah, great. It must be good evening there. So great to see all of you, and thank you for joining today. I'll talk about convergence of AI, simulation, and HPC, ultimately leading to this revolution of AI for science, right? So how do we incorporate the most exciting developments in AI to tackle some of the hardest scientific challenges? I think that confluence can create a lot of breakthroughs, and we're just getting started there. So indeed, I don't need to motivate anyone here by saying that AI is perhaps the most powerful technological force of our times, right? Going from standard tasks such as computer vision and language to now scientific problems, especially thinking about drug discovery, right? Ways to fight the current pandemic, embodied AI for robotics. We are now breaking new ground with AI, and that is very exciting. And the models have also tremendously grown. They have grown exponentially over the last decade. And now we are in the regime of billions, if not trillion parameter model. And so this kind of impressive growth, right, is the new Moore's law. We have the model complexity doubling almost every 2 months, which is mind-boggling. But what created this revolution is not just the algorithms, right? So neural networks have been around for a long time, but the current revolution of big data, having the internet to easily collect data and the compute infrastructure and the parallelism of GPUs is what enabled this revolution. And this is where it could be challenging for many scientific problems, because in many cases, you do not have a lot of data. And many of the traditional methods have been on CPU and not parallelized or not easy to parallelize. So that's where the traditional HPC and scientific simulations have had challenges in utilizing these developments. And but now it's a prime time to ask how AI could augment or even replace some of the traditional methods and get us the full gains of this revolution for scientific problems. And at the same time, indeed, the HPC has grown tremendously, right? We now have supercomputing machines in the regime of exaflops. And this is where it's no longer looking at very high precision computations, but lower precision computations. So that's what we think of like exascale AI, because AI requires much fewer bits compared to traditional HPC. That is, could be as much as 64 bits. And here we are investigating 16 bits and so many practical models, but also going all the way down to 8 bits or even further down. And some of the research we've been doing is looking at logarithmic representation where you don't need the mantissa and still you can get good performance in these models. And so that aspect of low precision computing, we are able to push the flops even further and make use of AI in a really good way. And so that's what has led to this development when we can utilize the developments done for AI also for scientific computation. And recently, one of the largest AI and molecular dynamics simulation, right, it used AI. And so we are now at the cusp of this new AI4Science revolution. And as we scale up further, it is exciting. Recently announced ALPS supercomputer will be having 20 exaflops of AI and be having both NVIDIA CPU and GPU tightly integrated. You know, a lot of traditional supercomputing, it was mostly CPU and hence not ripe for parallelism to the scale that GPUs can. And once we had GPU machines, this exchange between CPU and GPU was still very expensive. And now with the latest one, that would be further tackled. And hence, these kind of developments in HPC can greatly benefit lots of applications, right? Weather prediction, climate change is perhaps one of the most pressing problems of our times, discovering new materials, drugs. And what I'll do next is to give you the algorithmic developments in these areas. I mean, do we just run standard neural networks, or is there a room for new algorithmic development? And as a researcher in AI algorithms, I think there is tons of room for new algorithms because these problems are not standard supervised learning with fixed training and test data sets that are from the same distribution. Right? In most cases, you want zero-shot generalization. You want to be able to extrapolate to new scenarios. And that requires more than the standard algorithms we have today. I mean, one example is predicting, climate change, which is a highly multi-scale problem. If you try to predict the climate of this Earth and that over the next few decades, it is a hugely multi-scale and challenging problem, right? So what people do is to break it down into several scales. For this example here in the climate project, to predict the cloud cover, there is the global model, in terms of like getting measurements, say, from satellites. But you also need to have finer scale cloud simulations, right? And then try to map the two. And how to match that is a challenging one, as well as running lots of these cloud simulations at the finer scale. So these are things that we need to tackle at scale. And what we need is fast algorithms, as well as those that can handle all these kinds of different scenarios, right? So it's not just a fixed data because you want to now try and extrapolate it to the future. We haven't seen the future. The data in future will be different from what it is today. And so these challenges make this very interesting and at the same time hard. So the foundation for all such problems, right, for most of such problems is partial differential equations. It's no exaggeration when Steve Strogatz calls differential equations the most powerful tool humanity has ever created. Indeed, everything from like fluid turbulence, if you want to design cars, aircraft, spacecrafts, how to make sure we can handle the aerodynamics well, or designing new materials, what kind of plasticity properties do we want in different materials, what kind of stress it is going to be subjected to. Thinking about all these aspects, we can model them as PDEs. So the equations are usually succinct and simple to write down. right? But what makes it challenging is that there is no analytical solution for all these complex problems. And instead you have to do brute force numerical calculations. And like similar to this climate problem that I mentioned, most of them are highly multi-scale. So you have to solve the problem at different scales and try to tie the solutions together. And that's what makes it slow and expensive. But all hope is not lost. What we do have in these problems is a lot of structure, right? So there has been a lot of beautiful theoretical developments in applied math showcasing interesting properties of this highly complex set of equations. For instance, for fluid turbulence, when we think about Navier-Stokes, right, we know that the solution operator lies in some low-dimensional space. So even though it is, showcasing this complex phenomena, and the input and output can be arbitrary sets, right? So you can have arbitrary shape of the vessels. You can have, it's not discretized, it's continuous. How do you, handle these kind of mappings in a tractable way? And that's what makes it challenging for deep learning to incorporate structure of such complex models. But we do know such low dimensional structures exist. So there is hope that we could possibly create neural network architectures that are compact and yet very powerful in solving these equations and can be much, much faster than traditional brute force computations that do not, exploit those kinds of structures. And that is indeed what led to this project on neural operator learning, which is an interdisciplinary project between my group and Andrew Stewart in applied math, Kaushik Bhattacharya in material sciences. And the way we want to formulate this problem is given a set of inputs, right? So you're specifying initial and boundary conditions. So the coefficients, right, give the initial conditions of a family of parametric PDEs. Think about Navier-Stokes. You're now having different initial conditions for Navier-Stokes, different boundary conditions potentially. And you want to be able to predict the solution in each such instance. And this is challenging because you could have different possible discretizations of your input, right? Because this is no longer just fixed to one discretization like what we see in standard images or standard data. So most of machine learning looks at discrete inputs, right? So in the sense that even the image is a fixed set of pixels. I mean, the values can be continuous, but the number of pixels is usually fixed. Or in the text, the length can be variable, but the vocabulary is fixed. And so these kind of mappings, it's either vector to vector or even tensor to tensor mappings, right, are of fixed dimension. On the other hand, what we require for solving partial differential equations are function to function mapping, because you would like the flexibility to be able to query at different resolutions, right? So if these are my input points at different resolutions or different shapes of my grid, I should still be able to solve the equation. And that's what traditional solvers can do, but they are hugely expensive. They cannot generalize from one to another and they have to start from scratch, right? And that's what makes it expensive. But it is challenging for neural networks to be able to learn because all the standard ones assume this fixed size input, fixed resolution, fixed grid, but we do not have that for these problems. And that's what necessitated the creation of a new framework. So let me now go through some intuitions of how we generalized neural networks that map from finite dimensional spaces to now infinite dimensional spaces to handle the problem of solving partial differential equations. So this is just a standard neural network, right? So in a standard neural network with fully connected layers, what you have is some linear function. And this, in the standard case, it's matrix multiplication, right? If it's convolutional network, you have convolution, which is again linear. So that operation is linear, but to make this network expressive, you combine it with some nonlinearity like ReLUs, and then you compose over several layers. So this is just the basic standard neural network, but this is powerful in the sense you get a universal approximator for all finite dimensional functions of that size because of this composition with nonlinearity. So now, if you want to extend this to infinite dimensional functions, what we want is to be able to replace this linear operation in finite dimensions to now acting on infinite dimensions. So essentially a continuous linear operator. And so one natural such linear operator is the kernel integral or the integral operator. And this is obtained by looking at what would the solution be if we had linear partial differential equations. So if you recall any of your applied math class, there is the basic heat diffusion equation, for instance, and that's a linear PDE where you can solve, you can have the solution be expressed as integration with a Green's function, right? So this is the Green's function. So we know what the solution structure is for linear partial differential equations. And so now to extend it beyond, what we can do is compose it with nonlinearity like ReLUs, and hence we now have a framework that can approximate any general operator, right? So it can now be handling infinite dimensional inputs, mapping to infinite dimensional outputs, meaning continuous inputs and continuous outputs potentially you can have. And that's what now makes it a general framework. Of course, we haven't yet specified how to solve this integral operator efficiently, right? Right now, it's conceptually a framework that is expressive and goes beyond finite dimensional functions. So now the next question is how to make this practical and actually do this well. But before that, just kind of, it's intuitive that this becomes a universal approximator. But yeah, we are able to formally prove that it is in the case that you can approximate any operator given this framework. And for operators such as the solution of Navier-Stokes, which is the fluid turbulence equation, we do know a lot of good properties. Earlier I mentioned that the solution tends to lie in low dimensional space, right? So hence you can expect to have a neural network that is small, compact. So you do not need a lot of parameters to express this solution operator. And that's what is so powerful about this framework, that it is mapping infinite dimension. It has infinite dimensional mappings, but it's still finite, right? It still can be compact in terms of the size of the neural network. So the next question is, how do we solve this kernel integral in a tractable way? And we tried different variations, but the one that worked the best for Navier-Stokes and other popular families is being the Fourier neural operator, which is very simple. What we are doing is, using the Fourier transform to solve the convolution. So if you recall your signal processing 101, if you took the class, or otherwise it's a simple thing to follow here, is convolution in the standard domain becomes multiplication in the Fourier domain. Meaning once you take the Fourier transform of the signal, you just need to do element-wise multiplication to solve for convolution. And so you can nicely solve for this continuous convolution by transforming it into the Fourier basis and finding a weight matrix that multiplies it. So hence this becomes very simple, right? So this operation now is nothing but taking the Fourier transform of the signal of your input, right, function that you input, and then learn this weight matrix So that's essentially mixing the various Fourier modes. But the output of it, we only keep the low frequency mode, in order to be able to take the inverse Fourier transform in a stable way. And after that, we compose with ReLU or other nonlinearity and repeat the process again. So think of this as now filtering in the Fourier domain, but composing it with nonlinearity means we can learn complex nonlinear PDEs. So that's the power of this. It's very simple and yet very expressive. And what we see, one intuition of why we need Fourier transform and just standard convolution will not do the best job is because standard convolution has small local filters. So for images, having this to detect edges is great, right? On the other hand, when we think about fluid flow, it's global. You have the dependence of, one part of the fluid, both spatio-temporally to the other. So when you have global correlations, you cannot just afford to have local filters. And that's why having this Fourier transform was such a game changer in this work. And so that's the overall simple framework here. And we can also add some additional bias term, especially if you have like non-periodic information. So that's kind of like just an additional detail here. And so this is one of the exciting outcomes, right? So what we see is this is the first method to be able to solve Navier-Stokes partial differential equations in the turbulent regime, be 1,000 times faster than traditional solvers. And the powerful thing is even training is not expensive. You only need to train this on coarse resolution data and directly evaluate it in terms of fine resolution. So this ability to do zero-shot super resolution shows that this neural operator has learned the underlying physics very effectively. And it's also able to train and test on the same resolution much more effectively compared to other methods. And it's able to capture the frequency spectrum, right? Even the high frequency components well, especially if you do the Sobolev norm where you also have derivative losses. And so this shows that the model is able to, right, generalize to higher resolution, be able to handle challenging turbulent cases. You can solve inverse problems with this, with the speed up, because you can have, this unknown initial condition, and you only have the temporally evolved final condition here. You want to be able to invert to the initial condition. And that's an ill-posed problem. And hence, when we want to do these evaluations, we can do that very fast now with the neural operator. And there's so many other problems we can solve with this method. Just very quickly showing this plasticity is a multi-scale problem. And by replacing the solver in the fine resolution or the fine scale, we can get a big speed up while maintaining fidelity. We can also do this for ultrasound imaging, being able to simulate how the ultrasound would propagate amidst the organs in the human body, and being able to get good, accurate solutions. We can also do this for carbon dioxide injection problem, which is a multi-phase flow problem, and model how we can store carbon dioxide and hence tackle the climate change as one of the possible solutions. And again, we found very good promising results, 10 to the 4 speed up over traditional methods. So we can also combine constraints with, which is the equation loss, with the data available for training. And this is natural, right? So you have the equations, and we so far didn't incorporate them, but we can easily incorporate that. And what that shows is it's still better to have this pre-training, like train on a set of data and equations, and then at test time, fine tune on the equation of interest. And there we see that we can get much lower error compared to training compared to learning from scratch based on only that one equation. So there is a lot of structure that is common to different equations in the same family, and this method is able to utilize that. And that's what you see here, the ability to get to low error while being able to also easily generalize across different problem settings, like different Reynolds numbers. Yeah, so I want to also look at some of the other challenging problems. I won't get into this chaotic systems much, but more to say that we can also capture in these highly chaotic systems where you cannot predict over the long-term trajectory, these methods show promising results there. And we can also relate this to transformers, because transformers are really a special case of neural operators. And hence, some of the recent work has been to also look at using Fourier transform as a way to have cheap attention mechanisms, which is an interesting connection. And on the NVIDIA side, we have SimNet as a good infrastructure toolkit for large-scale implementation of such models to be able to solve partial differential equations at scale. Yeah, so the idea is, what you saw here is a framework for operator learning, where we remove dependence on a particular discretization or a particular grid style, and instead think of that as mapping continuous functions, right, to output solutions that are also in continuous functions. And this way you are able to handle any arbitrary discretization at test time. And so this way we can afford to train just on low resolution data and still be able to generalize to higher resolution evaluations. And so we are seeing a lot of promising results here. And in future, we are working towards even scaling up to more challenging problems. So before I get to some of the other examples of AI4Science, I do want to take the break and pause here and take questions and see if there are interesting ones.
Yes, thank you very much. We have actually one question from the audience, which says, how does your method compare to radial basis methods?
Yeah, so the idea is we can use all kinds of different bases, right? So, and that's problem dependent. I think for Navier-Stokes and the problems we considered, Fourier was very powerful. But yeah, there's certainly room to try out other bases and see if that further leads to improvement.
Thank you. And the questions are coming in.
Yeah.
So there's a little bit more general question here that says, how do you train the model? And I think what the person wants to know is, what is the data set, and maybe also some details on the implementation from an engineering perspective?
Yeah, the data set is a set of different initial and boundary conditions, and pairs of that with a solution, right? So you get the initial and boundary conditions of the PDE family and the solution pairs. So you train that to, could be the L2 laws, could be the Sobolev norm that I mentioned. You could also add the equation laws as physical constraints. And so those are the variants we did, and we did something like just 4 or 5 layers of the network, and that was already sufficient to solve the videos that I just showcased with Navier-Stokes. So it really depends on the setting in terms of the size of the model, but we've seen promising results even with small models.
Thanks, and maybe a follow-up. If I understand it correctly, the ground truth training data then comes from a very trusted traditional model. In the case of Navier-Stokes, I would say.
That's right. That's right. Although in the extension of the method, the PINO, where we also have equation constraints, if you have no data for training, you can still train this model on just the equation laws, right? So, find a solution that satisfies these equations. And that still gives good, solution in many of the problems, although it'll be slower to train because we don't have the actual data mapping to solutions.
Okay. I guess I'll ask some questions about that later, but there's more from the audience. And the next question would be, any thought on wavelet transforms and neural networks, please?
Yeah, so indeed, and I think there have been attempts to use the neural operator with wavelet transform. And that's, I think, again, right, the same aspect. If you're, the flows that I showed you are fairly smooth. They don't have sharp discontinuities. If they do, I think the wavelet transform would be better than Fourier. So it depends again on what is the nature of the equation family that you're looking at.
Right. Like, so what we would say, different equation families, different inductive biases.
Exactly.
Yeah. Thank you. And so can you also model higher order differential equations? For instance, oscillatory systems is what one person asks.
Yeah, I mean, these are also, right, these are nonlinear PDEs, right? And so similarly higher order, this is a universal approximator for any operator. So in that sense, it need not even be a PDE, right? So you could just have data and you don't know the model. All these cases we can handle. And the oscillatory systems, I did have results for the chaotic regime, like, this KS equation. Also Navier-Stokes is chaotic, meaning if you, make small changes here over a long time step, right, the trajectories completely diverge, what we call the butterfly effect. And so these are inherently unpredictable systems. So, we cannot hope to precisely recover the trajectory over a long time step. But instead, what we guarantee is the ability to learn the invariant measure, right? So we do know, even though these systems are chaotic, many of them have well-defined attractors, in some cases, even a single attractor, right? And hence, because of this convergence to attractors, right, even if you have like some, small local errors, you could still potentially converge to these attractors. And that's what we show, that these methods are able to do that.
Thank you. And does the neural approach have any sort of edge in this case over other methods?
Yes, you could also, you can do the standard recurrent neural network and other frameworks, right? The challenge is if you do a recurrent neural network over a long time period, and this is an unpredictable system, you will either have collapsing or explosion of gradients. Whereas we do not have this, because we only learn the small time step evolution and then just compose it over the long time period. This will not give the precise trajectory as the ground truth, but it will preserve the same statistics.
Thanks for your answer. And then there is the last question. How do you solve the continuous operator at each level?
Yeah, through the Fourier transform, right? Because the continuous operator at each level is convolution, and in the Fourier domain, that is just multiplication. So we are learning that multiplication matrix and then the mixing matrix. And then we are also only filtering out and keeping the low frequency modes. It's a good regularization for our training.
Okay, thanks. Actually, more questions coming in. I don't know if you should save them for the end.
Yeah,
or just
no,
continue.
that's fine.
Okay.
Because I was going to just show other snippets of other things that are quite unrelated. So it's better to focus on this too and spend all the time here. I'm fine with that.
Okay, thank you. So then the next question is it possible to apply the neural operator to a static case? For instance, the time variable has no influence.
Yeah, it could be on any arbitrary data set, right? If you think in the most general sense, an operator maps, some infinite dimensional inputs to infinite dimensional outputs, right? It need not even be in the same domain. The input and output can be different domains. So in that sense, the most general framework incorporates all this. Now the question is the inductive bias for these different domains. What do you use to solve the continuous operator at each level, the linear operator.
Okay, thank you. Good, and it seems we have answered all the questions, even though one is not marked as answered. Yes, now it is. Okay, good. Okay, thanks. Then I think it would be good to go to the next slide now. Right?
Great. Yeah, so, in the remaining, I guess, 10 minutes, right? Or how much time do I have?
We have another 25 minutes, I think.
Oh, okay, I didn't, okay, because, right, we started later.
Yeah.
Got it. So, yeah, so let me now get to some of the other examples of AI4Science, right? Some of our recent works kind of, again, asking the question of this zero-shot generalization. So in this work, what we did was to say, let's not limit ourselves to the resolution on which we train these models, because in principle, we should be able to solve the partial differential equation at any other resolution, at any other kind of grid, right? So, and that's what led us to creating this operator-based learning. So in many other domains, there are similarly such zero-shot generalization requirements. And one such instance is drug discovery. So how do we, search for drugs in this enormous space, right? So it's 10 to the 60. So this is just mind-bogglingly big. So you can't possibly go and look through every molecule. Instead, what we are doing currently is mostly trying to find small variants of known drug molecules, right? So most of the drug discovery tends to be in a tiny part of the space. Indeed, and it's such a long, right, process, and this is only part of it, right? So what we are looking here is once we have this candidate drug molecule, you want to look at its docking properties, simulation, like this molecular dynamic simulation, right? And ultimately human trials. So all kinds of different right, stages, and that's why it is hugely expensive and prone to failure. So is there any way to, right, incorporate machine learning in all these stages? And indeed, that's a huge endeavor. And what I'll show you now is to be able to, like, even in the first stage, like, how do you pick good drug candidates, and how do you get precise measurements of its properties? For instance, for being able to determine this docking, whether it's going to bind or not, right, is completely determined by its quantum mechanical properties. So the Schrödinger equation is the fundamental equation that governs, right, if you recall your quantum mechanics, the energy of this molecule and every other property. But computing this is exponential time. So even for a molecule with small number of atoms, say 50 to 70 atoms, we are already beyond all the computation on this earth, right? So this is why it's impossible to do precise computation for protein-like molecules. And the question is there a way to make this much more efficient? Can AI be used to speed up computing the properties of these molecules at the quantum mechanical level? And that's where the project we have in collaboration with Tom Miller's group at Caltech here is advancing. And what we see is the ability to combine traditional features with machine learning models like graph transformers is powerful, right? So what we want is transferability, right? So I told you that trying to compute this Schrödinger's equation is untenable even for moderate-sized molecules. And instead, what people do is these approximations called DFT, that are like considered the gold standard for these computations, but they're still extremely slow, right? So what we want is to be able to train a machine learning model to replace these DFT calculations, but only utilize small molecular data for training. So if we can train just on small molecules and at test time evaluate on large molecules, then we have a zero-shot generalization. So again, the goal is to be able to, have small amount of computation for training, because training data is still done with traditional methods. So we want to be able to do that on only small molecules and directly generalize to large molecules like proteins. And to do that, we cannot expect, if we just did like say a graph neural network, it would directly generalize, right? It is impossible because it doesn't know any of the domain constraints or knowledge. On the other hand, these molecular orbitals are essentially computations that look at dependencies between atoms in the molecule. And these computations that underlie based on this Schrodinger's equation are universal, right? They're true for any molecule, whether it's protein or whether it's these small molecules like the water molecule. And that's what makes our method transferable, because we use first the molecular orbitals as the starting point. And on top of it, we are building these graph neural networks, graph transformers. And so this hybrid method makes it fast and hence also transferable. And we can also incorporate all kinds of symmetry constraints. For instance, we know rotational symmetry. You rotate the molecule, properties like the dipole moment should also rotate accordingly. This kind of equivariance we want our neural network to incorporate. So in also handling this is really critical. And so that's what we are able to do. And yeah, so I won't get into the details of this neural network architecture, but what it kind of does is to be able to take quantum features like these orbitals and be able to, maintain the equivariance throughout the network so that the symmetry is preserved, like rotational symmetry is preserved even as you process through the neural network. And what we see here is, sorry about this here, 1,000 times speed up over the traditional methods, but still get very accurate solutions. So as I mentioned, the DFT is pretty much the gold standard for these computations, but they're very expensive, right? So you have now 1,000 times speed up with our method and still the same accuracy as DFT, and do this on large molecules. So we are able to test this on molecules that's 10 times or more bigger compared to the training data. And so that's the benefit. And also compared to other methods, we're also efficient in our training samples. So we do not need as many samples because we are using the symmetries of the system. We are using the orbital information, which is invariant. So these aspects also make it very powerful in terms of zero-shot generalization. And the benefit of doing this, right, is to be able to learn a powerful representation for molecules. By this, we can then predict any kinds of chemistry properties. For instance, here, we are, I think, looking at some kind of a binding, and sorry, the details got missed here. Our method is much better in predicting that compared to even the traditional DFT calculations, because they are not learning these kind of predictive properties directly. Yeah, so this takeaway here is that, again, with zero-shot generalization, what we require is some kind of domain constraint that is invariant, right? So thinking about this orbitals, it is invariant across all molecules, whether it's small molecules or large molecules like protein. And if you start with that as your basis, you're then having high degree of transferability. The other is symmetry properties. Being able to incorporate symmetry makes it also a lot more powerful in being able to predict the properties well. So I can take some questions here before I show another work also in the realm of AI4Science. Yeah, so in terms of the confidence or the uncertainty of these methods, so far we haven't looked into it, but certainly it's possible to add this. In another line of work, what we showed is a robust method for confidence calibration, even under distributional shifts, right? So we took the case of trying to learn on synthetic images and going to the real images. So this domain adaptation problem. And we know standard neural networks are overconfident when they make errors. And they're especially wrong if there is a domain shift between training and test data. And so we have distributionally robust methods that look at estimating the density ratio between the source and target data and use that as a way to predict the confidence in a calibrated way. And so I believe those kind of methods can be useful here to also have uncertainty, but we haven't incorporated it so far. Yeah, so the scope of the models here, the details are in the paper. So I think there's QM9, and there's also new data sets collected by the Tom Miller's team itself that is even bigger. So I think in the latest one, we have about 2.3 million training data. That's the largest training data set as well. But we've done that also on all kinds of these drug-like molecular repositories, both for training as well as for evaluation. Yeah, so right now we've limited to the drug-like molecules, but in future, we want to also evaluate it for other molecules because this is universal. Yeah, I hope that answered. Mm-hmm.
Also a question for me, is there like a limit to the molecular size that this can scale? Because proteins, they can have tens of thousands of molecule atoms, for instance.
Yes, right. I mean, in principle not, right? But again, at this point, we've been evaluating it for drug molecules and we are continuously scaling up. And so looking more at specific use cases of binding and seeing how the predictive power is.
Okay, thank you.
Great. Yeah, so given this, let me now show another exciting area and a very futuristic in the sense, right? We still don't know what is the future of quantum computing. It's very tantalizing in terms of the possible speedups, but also extremely fragile, and the hardware, right, can barely do like tens of qubits at this point, and again in very specific cases that are noisy. So yes, a lot of possibilities, but also a lot of challenges here. And I'm not in the realm of building hardware for quantum computing, but instead we are asking how can we utilize all the tools we are building for machine learning to also simulate quantum systems well? Can we use the parallelism of GPUs for effective simulation? And can we speed up this simulation? And can we use machine learning to design what we call these nonlinear quantum algorithms that use quantum circuits, but also do nonlinear optimization on top to be able to fit to the problem at hand? So in the sense, you're now optimizing for the quantum circuit that you want to use to solve your given problem. And lots of challenges, like I mentioned, right? So in the nearer term, we have to deal with all these errors. so highly noisy and very kind of connectivity is also a problem. So not like a standard neural network, you just build everything together and just run it. We are nowhere near that. And so the set of problems we want to focus on is what's known as the variational quantum computing, which is useful for moderate entanglement. So the idea is, the holy grail is this highly coherent quantum systems, right? We can break cryptography, we can do amazing things once we have that. But that's very, very far off according to all experts, right? So instead, the nearer term is we're going to get quantum circuits that are going to be extremely noisy, that only have moderate or small amounts of entanglements. Is there still a benefit to using that over classical computing, right? And the counterpart of that is, can we build efficient classical simulation algorithms for simulating these kind of variational quantum computing? And so that's the problem we wanted to tackle. And because, this entanglement of the extreme kind is very hard to achieve, but moderate entanglement is much more nearer term and realistic. And what we see is this is where the work I've done with tensors earlier is very relevant, because we can build moderate to low entanglement quantum circuits using different kind of tensor representations. And the tensor train or the matrix product states is perhaps the simplest one, because you're only connected to the nearest neighbors. So these are fairly low entanglement quantum systems, right? So this is still quantum, but it's not global entanglement, right? Like the sycamore, it's very local entanglement and low entanglement. So the question is there a role for even such simple quantum circuits to have a quantum advantage, right? Do we expect these such quantum circuits to do well on some standard benchmarks? And one of the standard benchmark is the max cut problem. Can we solve arbitrary max cut problems, which we know is NP hard, very well with quantum circuits? And so that's why we are mapping this max cut problem to the Hamiltonian of this tensor train, or essentially a tensor ring, because you're kind of tying that together. And so this is a low entanglement quantum system. And once we do this mapping, can we then use this variational optimization to be able to extract ultimately the solution for max cut from this quantum circuit? So essentially, you're optimizing your quantum circuit to be able to provide the solution to this max cut problem, right? So, so what we now want to do is to enable this well. And what we have is different forms of nonlinear variational quantum algorithms that can do this mapping efficiently. So in one of them, what we did was to be able to simultaneously map two different graph problems to one quantum circuit. And this makes it more efficient because you're kind of packing in twice the amount of computation needed into one quantum circuit. And this is kind of done because in the quantum circuit, you have like these, what we call the poly half spins or the XOR Z spins. So you can simultaneously encode multiple problems into one. Or the counterpart is to be able to have a quantum circuit with half the number of qubits as the size of the graph, because you can encode them into these X and Z spins, these different nodes, and be able to solve the problem and be able to do that with high accuracy. And so Tensorly is the toolbox we are developing for such quantum circuit simulation, but also for neural networks, like being able to have highly optimized neural networks with good inductive bias. So, this toolbox is, you can run it with PyTorch, but also NumPy and other Python-based frameworks. So makes it very easy to define layers as tensor networks or tensor operations and build that into your neural network. So this is open source. I encourage you to go and check it out. And when it's combined with primitives like QQuantum, then we get very powerful scaling here. So any questions here? Yeah, so, so that was just a kind of a quick overview on what we can do with quantum circuit simulation on GPUs well, and designing good, simple tensor network representations for quantum circuits that can solve hard optimization problems. The other side of the coin here is to be able to also use simulations for training good AI models, such as in robot learning. For instance, this is the actual BMW factory, right? Getting data from this is going to be very expensive. But if we have a good simulation where we can train our models on how to navigate, right, this factory floor, how to grasp different objects, then we can greatly enhance our training data. And so that was one of the works we did over the last year, was to show this in simulation, be able to train the robot to handle all kinds of challenges here, right? But the thing is, we didn't learn these low-level primitives from scratch, but instead, only trained the reinforcement learning to learn how to mix them up together well, right? So here you see that as it's able to walk, it's learning how to mix the primitives well. And so having this means it's able to do zero-shot generalization. A baseline that's not having those primitives will not be able to handle, say, a frictionless surface, but the reinforcement learning algorithm can, this is a test time, right, when there's no further training. It's able to do that well. And it's also able to transfer to the real robot. So again, this notion of zero-shot generalization requires us to have a modular setup where we do not learn the primitive motions from scratch, but only learn how to mix them. And hence the robustness built in these primitives will help us do sim-to-real generalization well. And the other aspect of zero-shot generalization is also to be able to handle safety conditions, right? So in this example here, the neural lander is able to land faster, but still maintain safety conditions. Whereas the traditional drone landing is slow, and because it's extremely conservative, you want it to be safe and not crash. Whereas the neural lander can do both. It has safety guarantees, but it's also able to land faster and be able to do good trajectory tracking here because it's learned a good model of the aerodynamics, which is very complex to otherwise get a model through traditional methods, but we are able to have a data-driven method here to do this well. Yeah, so in conclusion, I think the AI4Science is the future of science. And what we've seen is several instances where there are hard requirements like zero-shot generalization, but also novel methods that can handle these cases. And I think there are a lot more exciting things to be solved in future. So happy to take further questions.
I think we have time for like one question, maybe, because we're running out of time. Any questions from the audience?
I would have maybe a more general question, because I find it really impressive how like this interdisciplinary approach. Mm-hmm. And I just wonder, it must be incredibly difficult to communicate both with quantum chemists and people that are doing other kinds of quantum physics. And I mean, can you comment on that? Like, how do these collaborations occur, and what are the difficulties?
Yeah, that's a very good point. I think, it is an investment, right? And it is going to take time to build a language bridge. I think one aspect that has really helped us at Caltech is we are small and very collaborative, and people want to be using the machine learning methods, and we're very curious and inquisitive, right? And we have students who take machine learning courses from all over campus. So I think having that kind of baseline knowledge of machine learning and for them to be able to communicate with us how to frame this as a machine learning problem, I think is an important starting point. Without that, it would be very hard to go further. For instance, I also have collaborations with the humanities group here at Caltech, the social sciences group, and their students are also extremely mathematically capable. They've taken my courses. They're now building these topic modeling at scale, processing billions of tweets very quickly on GPUs. So that kind of ability to cross barriers and be able to handle algorithm building, programming, being able to scale up while understanding that core domain, I think is an essential skill that helps us achieve these kind of results here.
I see. So because all these disciplines, they speak different languages, so to say, but the connecting languages is machine learning.
I believe so, at least. That's I think we, at Caltech, we do have, even in our CS1, like enough kind of machine learning background, and in the general courses that are taught in the first and second years, there's a lot of kind of at least exposure to machine learning. We also have the data science major and minor across campus. I think building that now for the new undergraduates is, I think, a great starting point, irrespective of their major.
All right.
Thank you
very good. Yeah, so unfortunately we're out of time, so we need to wrap up here. So thanks again, Anima, for the very interesting talk. And thanks again, Edgar, for moderating. And thanks to everyone for attending and for all the interesting questions that you had. All right, see you in a while. Take care. Bye-bye.
Thank you. Bye.